Okay, so let's have a look at some multiple choice questions. I'm going to do 5. I'll give you a chance to have a go yourself, and then I'll go through the answers. Hopefully this will help you with your revision. Let's have a look. So question 1. Okay, a radio transfers 30 joules of potential energy to 27 joules of useful energy. What is the efficiency and energy loss for this radio? There are your options, A, B, C, or D. What do you think? Okay, so this is a question on efficiency. We're talking about useful energy compared to some energy that we've started with. What is the efficiency? Efficiency is all about comparing what you get out with what you put in. Okay, we could say we've started with 30 joules of energy. We've done something and we've ended up with 27 joules of useful energy. Now, law of conservation of energy suggests that, states that what we put in at the beginning, we need to be able to account for afterwards. Okay, we can't destroy energy, we can't create it, therefore we must be able to account for it. We've got 3 joules missing. Okay, that is what has been lost somehow or wasted. Okay, any energy that is not useful, we can describe it as wasted. So we can straight away state that we've got 3 joules of wasted energy. That gives us A or C. Okay, we can quantify efficiency using this equation here. If we want it as a percentage, we have to multiply that by 100. Well, we've got some numbers. Let's see what we get. We've got 27 joules out. Okay, we had 30 joules in. Multiply that by 100. 27 divided by 30 is going to be multiplied by 100, and that does indeed give us 90%. So that is giving us C. Okay, 90% efficiency, 3 joules lost. Answer C. Okay, question 2. Let's have a look. We've got a boy kicking a football. He's got a mass of 400 grams. What is the potential energy of the football when it is 0.8 meters above the ground? Use the constant gravitational field strength G equals 10 newtons per kilogram. A, B, C, or D? Okay, let's have a look. Push that over there. Let's see what we've got here. We've got some quantities, so we're going to write out here. We've got a mass of 400 grams. We have got a potential energy of something, okay, but it's asking us what that is, so we don't know. And we've got 0.8 meters above the ground. That's a distance, but distance above ground we would generally describe as height. So I'm going to write that as h. And we've got this value of G, that equals 10 newtons per kilogram. Units wise, okay, I need to check my units. Are we happy? Not really, because I've got grams here and I've got kilograms in there. We need that to be, we need a consistency here. In physics, we use kilograms, so I've got a conversion. Okay, I know that there are 1,000 grams in 1 kilogram. So if I've got 400 grams, I've got 0.4 kilograms. So mass is 0.4 kilograms. Okay, I need to make sure I use that value, not the 400. Write it down because there's a mark in it for you. Okay, show that you've made that conversion. Now, I need to recall an equation that contains all of these variables. I've got E, M, G, and H. I'm going to recall that energy equals mass times gravitational field strength times height. Substitute my numbers. Well, I don't know what E is, so I can't substitute a number for it, but I do know it is E for gravitational potential energy because it's in the question. Okay, so it is not a question mark. It has a letter. It's got an identity. Mass, I do have a value for, and I'm going to use my converted value, 0.4. I've got a value for G given to us in the question of 10, and I've got a height in meters. That's the correct unit, 0.8. If I solve that, I get 3.2 joules. So answer B. Question 3. National Grid transfers energy efficiently using high voltages. Why are high voltages more efficient? So we're thinking about efficiency again. A, high voltages produce a high current which heats wires less. B, high voltages produce a low current which heats wires more. C, high voltages produce a high current which heats wires more. Or D, high voltages produce a low current which heats wires less. What do you think? Okay, we're talking about efficiency again. Okay, National Grid, that's how we transfer our energy from the power station to our homes. We want that to be as efficient as possible. Energy is expensive. We don't want any to get lost along the way. Okay, so we're looking for high efficiency. How are we going to achieve that? Well, these answers, we've got an option between high or low current. We've got options between heating the wire more or less. Okay, now we want to transfer energy usefully for it to be efficient. Okay, heating the wires along the way, those wires that are up on those pylons, but from pylon to pylon, we don't really want to be heating those wires up. Okay, it might help the birds stay warm, but we don't want to be heating those wires up because that would represent a loss of energy from the system. Okay, that would reduce our efficiency. So we do not want to heat the wires. So we want to be heating the wires less. So that suggests either A or D. Okay, so how do we heat those wires less? We need to think about the current. Is a high current going to give us less heat, or is a low current going to achieve less heat? Now, current in a circuit, if you think about those electrons within the conductor, okay, those electrons are going to be colliding within the conductor with the ions. So high current, okay, if those electrons within that conductor are moving quickly, they're going to have more collisions. Okay, those electrons are going to collide with the ionic lattice more frequently, and that's going to generate more heat. Okay, so that's not what we want. We don't want more heat. So it makes sense that if we have a lower current, we have less collisions, and therefore less heat. And that looks like our answer. Okay, we want the answer that suggests we're going to have a low current that heats the wires less. So that's answer D. Question 4. Which statement describes nuclear fusion? Okay, so we've got 4 options there. 2 hydrogen nuclei formed, joined to form a helium nucleus. The helium nucleus joins with a hydrogen nucleus to form an alpha particle. Uranium nuclei split and produce high energy neutrons, causing a chain reaction. Or 2 helium nuclei join to form a hydrogen nucleus. What do you think? Okay, well, fusion. Okay, think of the word fusion. We're fusing things. That means we're joining them together. Okay, fusion is about joining things together. So our answer is not going to be C. All right. Now let's have a little bit more detail on this. We're talking about isotopes of hydrogen. They join together to form helium nuclei. Okay, we've got 2 small nuclei that join together to form a larger nuclei. Okay, so it's looking very much like answer A. Okay, but let's have a quick read through to make sure that there isn't anything else that might be feasible. A helium nucleus joins with a hydrogen nucleus to form an alpha particle, then alpha particle is a helium nucleus. So that's like saying a helium nucleus joins with a hydrogen nucleus to form a helium nucleus. It doesn't make any sense, so it's definitely not B. We've already discounted C. Looking at D, 2 helium nuclei join to form a hydrogen nucleus. Well, helium nuclei are bigger than hydrogen. It doesn't really make sense that you can have 2 large nuclei joining to make one small one. That doesn't make any sense. So D doesn't make any sense either. Okay, so A all day long. Okay, then question 5. Which row correctly describes the domestic electricity supply in the UK? Now, without me revealing the options, I wonder if you know the answer. Okay, let's have a look what the options are. A, B, C, or D. Have a look at those. What do you think? Okay, then. So this is something you kind of have to just know. It's hard to deduce it from the information provided. So let's just know that the domestic supply in the UK, first of all, it's alternating current. Okay, that's AC. It's a continuous wave of positive and negative potential difference, voltage. Okay, it's a continuous wave. Waves have a frequency, and they have a frequency of 50 cycles per second. Okay, and the voltage, the potential difference is 230 volts. All right. The alternative is DC. Now, many appliances at home do run on DC. Symbol is more like that. It is not a continuous wave. It's called direct current. It does not have a frequency, and we can use transformers and electronic devices and circuitry to convert our supply to whatever direct current we want for each individual device. So, for example, when you charge your phone, you're probably charging your phone on 5 volts DC. You need a special plug, a special transformer to convert your supply at the socket to what your individual device wants. Okay, but our answer for domestic supply is going to be A.